Swayam Prabha. Digital India. Educated India.
I had started on commutation overlap. So I said that this will come into picture when the source inductance is not negligible. If I am going to have a perceivable value of source inductance and if the current is continuous. If the current is not continuous, then also there is no question of the current getting transferred from one phase to another, right? So we are looking at two things simultaneously. One is the DC link current has to be continuous. For every 60 degrees it should not touch down to zero. And the second thing is that the source side inductance is of perceivable value. So what we actually drew was something like this. I have the three phase sources maybe coming up from the grid. Maybe I use a transformer to step it down, and the transformer's leakage reactance I am representing in the form of source inductances. I am neglecting the resistance because that doesn't play a vital role in making sure that the current continues. So this is the source inductance value. I am assuming that all are balanced, so I am assuming them to be LS, and this is VAN, and this is VB, and this is VC with respect to the neutral. Of course, this is the neutral, supply side neutral, right? Now this is connected to the fully controlled converter. So I am showing as though there are three sets of devices. It could be diode, even then you will see commutation overlap, but I am just taking thyristors. That's it. And we are going to have a load on this side which has to be at least RL because the current has to be continuous. Let me probably show it as a DC motor drive, it doesn't matter because that is also equivalent to having R, L and E, all three of them in series. Now this is A phase connection, this is the B phase connection, and this is the C phase connection. Let me write down the same numbers as what we write down normally: 1, 3, 5 and 4, 6 and 2. And I call this point as P and this point as Q, if you may recall. And we were talking about the current getting transferred from device number 5 to device number 1 because I am firing one at a firing angle of alpha, right? So the current is getting transferred from C phase or device 5 to A phase, which is actually device 1. This is what we said. So when it is getting transferred, we said that as long as we didn't consider the source inductance, abruptly the current could get transferred. That's what happened earlier. But now the current cannot get transferred abruptly because LS will not give up the current. It has some stored energy. It is not going to be able to give up the current. And if it is not giving up the current, we are going to have both 5 and 1 conducting simultaneously as far as the positive side is concerned. And in the negative side, of course, I have assumed that 6 is already continuing to conduct. So initially the combination was 5-6. Now the combination should have been 6-1. But because 5 and 1 are conducting simultaneously, I'm going to have all 3 devices conducting simultaneously. So I'm going to have from alpha to alpha plus mu. This is the duration. I'm going to have 5, 6, 1 conducting simultaneously. And we call this interval is called the overlap interval. Because I'm having an overlap between A phase and C phase, which I should not have had if the source inductance effect was not perceivable. So this is what is the overlap interval. So we first of all drew the diagram, which is the equivalent circuit. If you may recall, we first drew VA, we drew LS, and then we drew as though one is conducting. Similarly, we had VC, we had LS, and we had 5 conducting, right? Both of them together is connecting to point P. And then we drew this load, and then from here we drew the reverse conducting, that is this device, which is device number 6, and then we had LS, and then we had VB, and this is how the current was flowing. So if I try to draw the current flow, this is the current flow direction, and this is going to be ID or DC link current, whatever is being carried, and this is going to be again ID. So obviously there is no variation in this DC link current, assuming that maybe the motor drive is operating at a particular torque value. So the armature current will not change. So I'm going to have ID to be a constant. So I can say I1, if I may call this as I1 and this as I5, I should say I1 plus I5 equal to ID. And we also said because dID by dt equal to 0, we are going to have dI1 by dt equal to minus dI5 by dt. This is one thing we wrote, right? We wrote a few relationships. So I'm trying to recall those things. One more thing we wrote was to actually draw the KVL equation here. This was the KVL equation that we wrote, from which, if you may recall, we got, so KVL equation for the loop containing VA, VC, LS, and then 1 and 5. We wrote that as well. And then that actually resulted in VAC equal to 2LS into DI by DT. This is one more thing we wrote, right? VA minus VC we wrote, and then LS into DI1 by DT. The other one was LS into DI5 by DT. And because DI5 by DT and DI1 by DT are equal to each other with opposite signs, we wrote that as 2LS DI by DT. This is what we wrote. From which we also said, from here, we wrote that VAC d omega t integrated between alpha to alpha plus mu. Because at alpha, I fired device number 1, and until mu, alpha plus mu, I had both the devices conducting simultaneously. So this is equal to, we wrote this as 2 multiplied by LS multiplied by DI, and of course we had to divide this by omega because we wanted to do it d omega t rather than dt, right? And I should have integrated this from 0 to ID because the current was increasing from 0 and it reached ID. This is what we wrote. So we wrote, so this is one equation which is of importance. This is another equation which is of importance. And the third equation, what we got from here was that VAC we could have written as Vm sin omega t because alpha is our reference. So VAC 0 crossing is our reference. That's why we are able to integrate from alpha to alpha plus mu. So we wrote this as Vm cos of alpha minus cos of alpha plus mu. This is what we wrote, equal to 2 omega ls id. This is what we wrote, right? 2 omega ls id, that's what we wrote. So now we'll have to, one more equation we wrote, if you may recall. Maybe let me write that also here. I think we wrote what is VPQ during the overlap interval. So we calculated first of all what is VP. So VPQ we wrote, which is the DC link voltage, we wrote as VAB plus VCB divided by 2. That is the average of just 5 and 6 conducting and 6 and 1 conducting. And then their average we took, and this is what we called as the DC link voltage. And we also got the expression for the difference in the DC link voltages between when there is no overlap and when there is overlap, right? So we should say that the difference in the voltage, that is the DC link voltage, when there is overlap and there is no overlap. There is no overlap. We wrote this as, when there is no overlap, it was VAB. When there is overlap, we said it is VAB plus VCB by 2. This is what is the difference. So we wrote the difference between these two as the overall difference that comes up in the DC link voltage for the interval between alpha and alpha plus mu. And this came out to be VAB by 2 minus VCB by 2, which is actually again VAC by 2. So we said that VAC by 2 is the difference that exists between whatever is the DC link voltage that would have existed without overlap and that is existing with overlap. So there is a good amount of drop in the DC link voltage. That's what we concluded ultimately. So let's try to draw the waveforms now corresponding to this, and let us see what happens in each of the cases. Right? So if I am looking at this as omega t, let me probably draw 2-3 waveforms together at the same time interval so that I have an idea as to how each of them is changing, right? So if I try to look at the DC link voltage, let me draw it probably for alpha equal to 60, because that is one of the waveforms which we are pretty familiar with. So I'm going to draw it for alpha equal to 60. For alpha equal to 60, I'm going to have a waveform somewhat like this. I'm going to have one, then second one, third strip. This is without overlap, of course. Fourth strip, and so on and so forth. This is how the waveforms are going to be, right? If I assume that I'm starting off with 5 and 6 conducting together, this is probably 5 and 6, then this is 6 and 1, this is 1 and 2, this is 2 and 3, this is 3 and 4, and so on, right? So obviously 5 and 6 together, I will have the voltage waveform to be VCB. This will be VAB. This will be VAC. This will be VBC. And this will be VBA, and so on. Right? These are all the waveforms that I would have gotten as the DC link voltage. So I should show this as VPQ. Am I right? And I'm talking this with respect to alpha equal to 60. I am firing 1 at this point. That's what it means. So that means I'm going to have this as alpha. Because every 60 degree I'm going to have a strip of voltage. That strip of voltage is 60 degrees, so and I have taken alpha to be 60, so hopefully this should have been my alpha, right? That is alpha. So VAC 0 crossing would have been somewhere here. This point is VAC 0 crossing. Am I right? Because with respect to VAC 0 crossing, I am calculating alpha and I have drawn the waveform for alpha equal to 60. So clearly that is the VAC 0 crossing point. Right. If there had not been any overlap, I should have gotten actually my current somewhat like this. The current should have increased abruptly and it should have gone until here as far as device number 1 is concerned. This is how the current should have been. Right? I am assuming ripple free current. Okay? I am not taking into consideration any ripple. So if I am talking about ripple free current, this should have been my A phase current. So I should say this is IA or I1. Similarly, I should have had my IA coming up in the negative direction somewhat like this when I am having 4 conducting. Right? On the other hand, if I try to draw, for example, I5, that is C phase current, I should have had the C phase current going somewhat like this and it should have abruptly come down to 0. It should have coincided with the red, of course, but I am just showing it so that you are able to see exactly I5 should have come down like this. This is all without overlap. So this should have been my IC, right? And IC should have started again at this point. It should have gone like this. So this should have been IC, negative side, without overlap, right? And now I am going to have the overlap. Because of overlap, there are going to be changes in the current waveform. So I will have actually the current not abruptly ending up in 0, rather it is going to come down like this. That is the difference that is going to happen as far as the current wave shape is concerned due to overlap. The same way, instead of IA rising like this, it should have risen like this. And it should have reached the maximum value of ID, if I may call this value as ID, within a period of mu. So I am calling this period as mu. Overlap interval where I am going to have 5 and 1 simultaneously conducting, right? And we are going to have the current somewhat rounded. It is not abrupt rise and abrupt fall. It is somewhat rounded, right? If I have more and more inductance value, this conduction interval must have been more because the inductance stored energy would have been more. So the current would have been more rounded. You get my point? So I'm not going to have the abrupt rise and fall. From abrupt rise and fall, it is going to become more and more smooth. The current has become smoother because of the presence of the source inductance. Right? Now, if I try to look at what happens to the voltage until this alpha plus mu, right? I have to look at the voltage. The voltage is going to be the average of VCB and VAB for this interval alone, from alpha to alpha plus mu. This is VCB, so I should take VCB further as though it is coming down. That is VCB, whatever I have shown in the dotted line, because I had just drawn VCB before when 5 and 6 were conducting. It is continuing to conduct and it is going to come up until here. But VAB is here. So I have to take the average between these two. So somewhere in the middle I should take, and this is the average. Whatever I am drawing, let me probably draw this in green or something, a little different color. So this happens to be the average between VAB and VCB. So this particular green waveform, whatever I have got, happens to be the DC link voltage. So this is going to be the DC link voltage which corresponds to this VAB plus VCB by 2. So I am going to have until 5, 6 and 1 conduct. Instead of getting VAB, I am going to get the average of VAB and VCB. The moment phi gives up, when the energy in LS is gone, it will go back to VAB. So my voltage waveform is, rather than going to have a single strip, it is going to have some wave shape like this. Similarly, I am going to have a wave shape like this. And again I am going to have a wave shape like this, and so on. You get my point? So I am going to have a reduction in the DC link voltage, and how much is the reduction is given by this particular area. Whatever is the area difference between the original value of VAB, which I should have gotten without overlap, and what I am getting now because of overlap, VAB plus VCB by 2. That difference amounts to, we calculated that as VAC by 2. So that is going to be really the difference between what DC link voltage I would have gotten without overlap and what I am getting with overlap. So that is a gross reduction, at least some amount of reduction in the DC link voltage. So if I want to really get what is the reduction in the DC link voltage, quantify it, then I have to integrate VAC by 2 from alpha to alpha plus mu. This is the area what I have marked as, the shaded area. The shaded area is VAC by 2, but that is going to be integrated from alpha to alpha plus mu. That is the amount of voltage that is getting stripped off from the DC link voltage. But this happens every 1/6 of the cycle. This doesn't happen once. Every time when I'm going to have the conduction transferred from 5 to 1, and then maybe 6 to 2, and again 2 to 4, 1 to 3. So every 60 degrees this happens. One positive device takes over and the other positive device goes away, or one negative device takes over and the other negative device goes away. Every time a new combination comes up, this particular voltage drop is going to take place. So this is the area under the curve, all right, but if I want to average it out, I have to say it has to be averaged over 1 by pi by 3, right? So I should say this is the average reduction in DC link voltage or DC output voltage due to overlap, right? So I am integrating this from alpha to alpha plus mu, but I am averaging it over the entire 60 degrees because this kind of drop or stripping out of the voltage takes place every 60 degrees. So I am averaging it over 60 degrees. If you may recall, the last time we wrote VAC equal to 2LS di by dt, we also wrote this particular thing, that is alpha to alpha plus mu. When I actually integrate it, it happens to be equal to 2 omega LS ID. But when I integrated VAC, so if it is VAC by 2, it should be omega LS ID. So if I may call this as equation number 3, I can say from equation number 3 in the previous page, right? I can write this as average drop in the DC link voltage equal to omega LS ID averaged over pi by 3. Because I have written the integrated value directly, omega LS ID. VAC by 2 integrated from alpha to alpha plus mu happened to be omega LS ID. So I am writing directly omega LS ID divided by pi by 3. So this I can write this as equal to 3 omega LS ID divided by pi. So this value of voltage has to be subtracted from the original value of average voltage we had calculated without overlap. The original value of average voltage we had calculated was 3 Vm by pi cos alpha. So from 3 Vm by pi cos alpha, if you subtract this much, this will tell you that that is the value of average DC link voltage that is available across the output side when I am considering overlap. When I consider overlap, this is going to be the reduction in the voltage. So I should say average DC output considering overlap will be 3 Vm by pi cos alpha minus 3 omega LS ID by pi. Sorry about shabby writing. Maybe I'll write it in the next page once again. Okay? 3 Vm by pi cos alpha was the original expression we derived where Vm is the line to line peak. Line to line peak. And what is given generally in your problems is line to line RMS. So you have to multiply that by root 2. Whatever you get as the RMS value has to be written multiplied by root 2 to get Vm. Okay? And this one is what we calculated as the voltage drop for every 60-degree interval. So that has to be subtracted. So if I try to look at the overlap, two effects now we have arrived at so far. One is I'm going to have the current rise delayed, because of which the current is rounded. Right? Current is not abrupt rise and fall you don't see in the current. You see the current being rounded. The second effect is reduction in the DC output voltage. Right? So, because the current is rounded, if I try to actually calculate the harmonic analysis or harmonic components in each of the current, that current is not going to be as abrupt rising or as abrupt falling as it was. So it is not as far away from the sinusoid as it was earlier. Previously it was very far away from sinusoid. Please understand, sinusoid never has any abrupt rise and abrupt fall. And you are reducing that abrupt rise and abrupt fall by having an inductance. You didn't put the inductance, it is there in the system. So that is essentially causing the current to rise and fall in a slower fashion. So the current becomes a little bit more rounded. Because the current becomes smoother and rounded, you would see that the harmonic content in the current comes down. So it is closer to the fundamental or sinusoid. So this is another effect which is a corollary of saying that the current has become smoother. Right? One more thing I had to say, one more effect is there because of overlap. Previously when I had the current somewhat like this. It was abruptly rising and I had 60-degree interval, dead to the world basically, another 60 degree of negative. You remember, I had always 60 degree positive current, 120 degree positive current, 60 degree in between zero current interval, another 120 degree negative current, and then again another 60 degree dead basically. But now, because of the overlap, I am going to have this current extending.